Okay, in this exercise, let's take another look at centripetal acceleration. So here we have an ultracentrifuge. That is a device used in oftentimes in the medical field for testing things. And it's a bit of a misnomer, centrifuge, not really centrifugal force, but usually you have maybe some sort of test tube, a bunch of test tubes that are attached to this ultracentrifuge and filled with like a blood sample or something, and then this thing is rotated very, very quickly, right, with some rotational velocity omega, and it's filled with sample something blood, and maybe I have a point over here, and this point is 2.5 centimeters. Just happens to be the length of this tube here, 2.5 centimeters from the axis of rotation, so it's rotating around this axis here, and we want to spin it so quickly, this omega, so that the forces acting on this point right here are, well, the acceleration, the centripetal acceleration is 400,000 times g, 400,000 times the acceleration due to gravity. Effectively, what that means is that the force that is pushing it this way, the centripetal force, is going to be equal to 400,000 times its own weight, right? So m times the centripetal acceleration, right? And so it's going to have a force of 400,000 times its weight. And then the things that can't actually have this force to push back this way due to densities and stuff like that, the material separates and the lighter things end up over here. Is effectively the way it works out. So we want to find out what is omega so that a point over here, 2.5 centimeters from the edge, has an acceleration of 400,000 g, so it separates here. And so let's write out kind of what we have given to us and what we're looking for. So what's given is that the radius is 2.5 centimeters. I'll convert everything to meters because we have g. Remember, when we use g, we have it memorized for 9.8 meters per second squared, right? So we're going to end up using meters and seconds, so we should convert everything to meters, seconds, etc. The acceleration, this is going to be equal to 400,000 times g, so 400,000 times 9.8, so this comes out to 3.92 million, so 3.92 times 10 to the 6th. This is meters per second squared. That's our centripetal acceleration. We're asked to find the omega, the angular velocity, or really angular speed that causes this, right? So the angular speed that causes this centripetal acceleration at that distance. And the solution, we have another formulation for centripetal acceleration. We've seen here centripetal acceleration is v squared over r, which is also equal to 4 pi squared r over t squared. We could find this linear speed, we can find the period, we know the radius already, but we can also use our next formulation for this. This is equal to r omega squared, or maybe I should have kept the same r here. I used a lowercase r. It's the same radius. This is r omega squared. The distance from the axis of rotation times the angular speed squared. And so, this comes out to the centripetal acceleration is r omega squared. This means that we have omega is equal to the square root of the centripetal acceleration divided by the radius, right? And so AC is equal to 3.92 times 10 to the 6th. This is meters per second squared divided by 0.025 meters square rooted. These meters actually cancel out, and it's not that it becomes unitless. Remember, we have meters over meters, but we put in radians for this as like a placeholder for angle. And so we have radians per second squared, square root of this. Square root of radians are actually still radians because it's actually unitless. And so the square root of second squared is seconds. And so then we have centripetal acceleration is, this comes out to be 1.25 times 10 to the fourth radians per second. And this is the centripetal acceleration, although, oh, I'm sorry, this is not the centripetal acceleration, this is omega. I'm really sorry about that. This is the angular velocity, which is radians per second, or units of angular velocity. So we are supposed to find this, though. They ask us to find omega in revolutions per minute, not radians per second. So we need to convert this. So we have 1.25 times 10 to the fourth radians per second times, we have 1 revolution per 2 pi radians. Radians cancel out, and we have 60 seconds per minute. And the seconds cancel out, and this comes out to omega is 1.2 times 10 to the fifth revolutions per minute. So it needs to spin at 120,000 revolutions per minute. It's pretty fast, but then that's a very, very large acceleration, right? So, and you can get the things to separate.